Today we are explaining the paper Scalable Training of Mixture of Experts Models with Megatron Core.
What is the paper trying to solve?
The big claim is that Mixture of Experts, or MOE, training creates a system's problem-dense stacks do not have. Total parameters grow much faster than per token compute, so memory pressure, cross-GPU traffic, and GPU efficiency become tightly coupled.
Why do dense model tricks fail here?
The mismatch is concrete. The paper cites DeepSeek v3 with 685 billion total parameters, but only 37 billion active per token, an 18x gap. Older MOE stacks also forced attention layers on expert layers to share one parallel mapping, even though they want different layouts. The base design is a four-step path route, dispatch, compute, combine. That modular split lets Megatron Core optimize routing, communication, and expert kernels separately instead of entangling them.
What is the router deciding?
The router maps each hidden state to expert scores, converts them to probabilities, and keeps the top K experts. Load balancing is the key. System's point hot experts do not just waste throughput, they also make training less stable. Older frameworks tie expert parallelism to data parallelism, so attention and MOE layers are forced to share one mapping. Parallel folding breaks that link. The paper's example keeps attention at TP equals 4 and CP equals 2, while the MOE side expands to EP equals 64 with expert TP fixed at 1.
Does parallel folding only help huge clusters?
No, the paper also says folding lowers the entry cost. A traditional CP equals 8 and DP equals 8 setup can force 60 for GPS, while folding lets CP and DP share the same GPU group, so the minimum can drop to 8.
Show me one memory trick.
Equation 1 is the standard MOE output. Y is the layer output, T of X is the selected experts. The paper writes it this way to show where a straightforward implementation creates an extra waiting buffer. Equation 2 moves the routing weight before the second linear layer. The output is unchanged, but the implementation can reuse buffers and drop a redundant activation tensor. That is why this trick cuts memory without adding compute. At scale, yes, the paper gives a DeepSeek v3 setup that would need 199.5 gigabytes per GPU on 100 before optimization, far beyond an 80 gigabyte device. Memory-efficient permutation, lower precision activations, recomputation, offloading, and SSTP plus expert parallelism each shave a different part of that footprint.
Does the memory storage stop at activations?
No, the paper says main weights and optimizer state at another 32.1 gigabytes per GPU in the DeepSeek example. Precision-aware optimizer storage can cut that roughly in half.
But communication still looks brutal.
That is the next wall. In expert parallelism, every MOE layer dispatches tokens to remote experts and combines them back. These all-to-all patterns sit in the middle of the training loop, so if they stay on the critical path, throughput collapses.
How do they cut that time?
They attack it two ways. DPP and hybrid DP cut redundant traffic, and one phone B overlap hides all behind compute. The result is concrete. Expert communication falls from 30 to 40% of iteration time to under 5%, with a 93% overlap ratio. Then the compute wall becomes visible. Small experts create small GEMs and lots of launch gaps, so the stack uses group GEMM, kernel fusion, CUDA graphs, and then ECHO plus stage dashing to keep dropless routing compatible with graph-based execution.
How does CUDA graph survive dynamic expert shapes?
That is why the paper adds sync-free kernels, ECHO, and paged stashing. ECHO clones hot experts to spare slots so overloaded ranks stop waiting. And page stashing replaces per layer worst-case buffers with one shared temporary buffer plus a stash that stores only the actual tokens used.
Low precision sounds risky. What keeps routing stable?
The answer is selective precision, not blind quantization. Routing-sensitive math stays protected while activations, communication, and expert GE. The paper reports roughly 10 to 25% end-to-end gains from FP8, depending on hardware.
Is the paper only about standard sequence lengths?
No, it also covers long context training. Once sequences get very long, attention can dominate instead of experts. So the paper shifts toward context parallelism, tensor parallel scaling, and text sequences with dynamic context parallel planning.
What results do they report?
The headline numbers are strong. DeepSeek v3 685B reaches 1233 and 1048 tera FLOPS per GPU on GB300 and GB200. QN3 235B reaches 974 and 919. And Section A reports 368 tera FLOPS per GPU for DeepSeek v3 FB8, training on 100. That matters because the same design works across models and across both Blackwell and Hopper systems.
What does the DeepSeek case study add beyond the table?
It shows the numbers come from systematic tuning, not one lucky launch. The best configuration differs by platform, but the pattern stays consistent. Parallel folding remains in place. Expert tensor parallelism stays at 1. And dispatcher, recomputation, and precision choices are tuned to the hardware. The lasting message is that sparse models do not become scalable automatically. Megatron core only gets there by code signing, routing, parallelism, memory movement, communication overlap, and kernel execution as one system. That is why this report reads like a practical training blueprint. That wraps up this paper walkthrough.